causes the thermal reaction to slow down, and the non-thermal acidic reaction to slow down. And it's not acidic, but it's a cathode and an anode. That reaction slows down when it gets hot. When it gets very, very hot, they get much hotter than 18650s. Okay, and they're more tolerant of heat than 18650s, but that's a whole nother story. So CR123s go down from 10 amps, and the amperage gets brought down to about 3 amps. And what's 3 amps times 3 volts? It's about 9 watts, which is actually still pretty decent. You can still put out quite a lot of lumens into a flashlight with 9 watts. Okay, 30 watts is ridiculous, but an 18650 is different. It goes up to 4.2 volts, and a good 18650 can put out not 10 amps, not 20 amps, but 30 amps. 30 amps times 4.2 volts is phenomenal. Okay, it is 30 times 4.2 is over 70 watts. Okay, so you're actually getting over 70 watts of power out of a single 18650. And there's only one kind that can do that, and it actually has a specific brand. It's called a Sony VTC6 battery. The Sony VTC5 and the Samsung 30Q, all those batteries pale in comparison to the Sony VTC6 battery. Panasonic makes a copycat version that is unbranded and that is not for sale. It was used for cars, automotive battery. In any case, but Sony VTC6 is a 30 amp constant drain. Now the voltage actually drops below 4.2. So it actually doesn't hold 70 watts for very long. It starts to drop. I think it goes down to about 3.5 or so, and it holds that for a little bit, and then it continues to curve down. So you get usually about 50 watts maximum from an 18650 for a continuous amount of time, and not for very long. We're talking maybe a couple minutes, and then it starts to go down. Flashlights with modern LEDs have anywhere between 100 and 180 lumens per watt. 100 lumens per watt means that if you're producing 30 watts, you should be able to have 300 lumens, which is 3,000. If your flashlight is producing less than 3,000 lumens, then it is not producing the maximum amount of light that the battery is capable of, period. Okay, and that is simply because 30 watts is pretty typical for most cells to be able to maintain, even down to like 20-30% power left. Okay, maybe not most cells, but the best cells, the Sony VTC6, for example. Okay, even when it's down at like 20% of its voltage, remaining, it still has around 30 watts. So it could still produce with an LED that only has 100 lumens per watt, you're still looking at 3,000 lumens. More efficient LEDs will have 180 watts per lumen if done correct with the right amount of voltage. Okay, the XHP 50.2 and 70.2 LEDs are the most efficient. They both have around 180 lumens per watt, to my understanding. Okay, the Luminous SST40 is relatively efficient, but it's also higher CRI, which we'll talk about later, but that's color rendering, and that does not improve. It severely decreases the efficiency. In any case, so there's this big myth. Flashlight goes down in power because of the battery. No. Now, there's a truth to that. Okay, several truths. One is anything with a AA, yes, it goes down in power because the battery can't maintain it. Okay, and a second truth to that is yes, if a battery is a low quality battery, it will not have the same output. The third element to truth in that is yes, when the battery is very close to being out, sometimes it's not enough wattage to maintain the very maximum mode of some flashlights. Okay, that being said, other flashlights that don't let it run the maximum, it doesn't mean it can't. It just means it doesn't want to push the battery at all because it's aware that that battery is at 3.1 volts or whatever. And if it pushes 1200 lumens, it's going to crash down to 2.9 volts very quickly. Another huge myth with batteries is that on the lower half of voltage, it has half of its energy, and the higher half of voltage, it has another half of its energy. And that's actually very incorrect, and actually is a myth that even flashlight, get this, flashlight manufacturers believe that 50% power has to do with 50% of the watts. Excuse me, 50% of the volts. But 50% of the watt hours is not in the bottom half. It's less than that. Okay, most of the energy in a cell is between 3.7, 3.8 volts or so, and 4.2 volts at the maximum. That has about 50%. The other almost solid volt from 3.7 down to 2.7, 10 whole points, 10 tenths of a volt or 1 volt is the other half of the energy. Okay? The answer why to that is obvious, because the amperage for the first half of energy is multiplied times a higher number. Okay, 10 amps, say, is what the current output for the battery is. That at 4.2 volts, 10 times 4.2 is, of course, over 40. And then you go down to 4 volts, and it's still 10 times 4, and that's 40 watts. Okay, and then you go down to 3.8, it's a little bit less than 40 watts, right? But once you get down to like 3.5, 3.5 times 10 is only 35 watts. 3.4 is only 34 watts. 3.1 is only 31 watts, and 31 watts is a lot less than 38 or 37 watts. Okay? And so you have this runtime above 3.7 volts, and then the runtime below. So usually nominal or whatever is kind of the halfway point of the battery. And the milliamp hours is taken as a measurement based on how long the battery can run on. Okay, the same amp output. And it's usually based on a very minimum output. And we're going to talk more about that. And battery myths, because right now what I'm really trying to get at is flashlight battery myths, not just battery myths in general. Okay, because the truth is, I'm going to get off track. So we're going to talk about that some other time. Point here is, with watt hours, with most flashlights, when they say 50% energy, it's actually inaccurate. It's actually 30% energy, because it's actually based on a voltage like 3.4 volts, which is laughably inaccurate, because that's basing 7 points of volt versus 7 points of volt. Okay, because 4.2 volts down to 3.4 volts is actually 0.8 volts, and take 3.4 volts down to 2.65 volts, and that again is 0.8 volts. But that isn't where half the power is. Half the power is 3.7 volts up to 4.2, and the 3.7 volts down to 2.65 or whatever. So that's a misunderstanding, and even flashlight manufacturers that make this light and stuff, they screw up voltmeters and they wind up measuring the wrong voltage increments, which is a real shame, because people don't understand how much power their lights can and do have. In any case, but we're gonna try to wrap this up relatively quickly here. There's a myth out there that 3.0 volt CR123 lithium one use, they just get one use, they're not rechargeable. These non-rechargeable lithium cells, that 2 of them have the same energy or even more energy than one 18650, and that is not true. Okay, that isn't true. They have less. Okay, they have about 8 watt hours or so, and a single 18650 will have at least 10 or 11 watt hours, as much as about, I think the best in the world is about 13 watt hours or so. Okay, 2 CR123s have at the very most 8, usually it's about 7.5 watt hours or so. Okay, or 7.500 watt hours, but that doesn't 100 milliwatt hours, but we don't use milliwatt, we just use watt hours. Okay, 121.700, the best ones have about 19.5 watt hours. The worst ones have about 15 or 16 watt hours, which is still better than the best 18650. Okay, another big myth with batteries, okay, that I've heard is that the 26650 still has significantly more energy than the 21700, and the actual answer is no. 21700s are built with a separate kind of technology that's typically used inside of them. Could we apply that to 26650s? No, we could apply it to 26700s, but there's some length limitations with 26650s that mean it's not really possible. So we actually can't apply it to those, and that's a whole nother conversation. But basically, 21700s aren't just, they actually have the highest energy density. So they have 19 watt hours for their volume, and I did volume calculations on some point, but basically 26650s can get 20, sometimes 21 or 22 watt hours, but they are more than 10% bigger, even though they can only get about 10% better performance. And that being said, most 26650s with that kind of performance are equally expensive to the 21700s that can produce 5,000 milliamp hours and thus 19,000 milliwatt hours or 19 watt hours. Okay, or 1900 milliwatt. Anyways, so 21700s, okay, are also more efficient than 18650s for their size. Okay, and I know this might be difficult to grasp because you might think, well, we'll eventually have 18650s that are the same. No, we won't. We could have 18700s that are the same, because that's just a tighter roll of the elements and using less mass. But 26650s will never have the same energy density as a 21700. Okay, or at least not for the next couple of years. All right. So 13 watt hours versus 19, maximum versus maximum. Okay, and then what happens with 18650s is they are about 20%, I think it is, 20% smaller in volume than 21700s. And the difference is greater with protected cells and unprotected. Unprotected 21700s are actually called 21750s. And unprotected 18650s are called 18700s because they have about 5 more millimeters of length. That makes them closer in size. Okay, so comparing protected cells, which is what most people have today, is different than unprotected. Unprotected cells, the difference of size is about 20%, and with protected cells, it's about 15%. 21700 that's protected is 15% bigger than an 18650 that's protected, and two unprotected cells, the unprotected 21700 is about 20% bigger than an unprotected 18650. But in both cases, they provide 30% more energy. So having 30%, okay, of 13,000 milliwatt hours, okay, or anyways, 13 watt hours, okay. 13, what's a third of 13? A little bit more than 4, okay. What's 13 plus 4? 13 plus 4 is 17. It's actually 19 watt hours. But I'm giving, I don't want to call it 40% more for a number of reasons.